Hey, welcome everyone. I'm Ken Claerbout, K4ZW, and on behalf of the Worldwide Radio Operators Foundation, I'm glad you could join us for this presentation. I was taking a look at the registration list before we got started here tonight, and we've got quite a few people signed up for this thing, and all corners of the globe. I've got the U.S. covered. I see down in Brazil. I don't know if K0MD is still in Chile, but he's on here. Hawaii, I saw someone in India, and probably a few other places in between. So it's great to have such a broad audience for this great presentation here this evening. I also wanted to mention that actually today the WWROF renewed the sponsorship for this webinar program for another year, so we're good to go. And as we encourage you on every presentation, if you haven't, go check out their webpage at wwrof.org and take a look, see what they're doing. If you can help them out, great. I'd love to have your assistance there. As most of you know, we do have a Q&A at the end of the presentation. You're free to send in your questions at any point, but we'll hold them until the end of the presentation just to kind of maintain the flow of things. So with that, I'm going to kick this over to the state of Indiana, someone who is no stranger to our webinar program, Carl Letzel-Schwab, K9LA. Carl, thanks for joining us. Go ahead.
Okay, hello Ken, and hello to everyone out there. Ken said I've got a great presentation, so you're going to have to bear with me. I got to make some revisions to bring it up to par here. But we'll do that on the fly, so that's okay. This evening I'm going to talk about solar topics and where we're headed. So let's see if this thing works here. It's been a while since I've been on GoToWebinar. Yeah, of course not. Let's see, how come it doesn't? Oh, there it is. It advanced.
Okay.
Okay. Yeah, I had to click on the screen. Again, just like I do for every presentation, thanks to the Worldwide Radio Operators Foundation, and especially Ken for setting up this webinar and all the many previous webinars. Let me just remind you that, you know, go to the website that Ken referenced. It's there on this page also. There are lots of previous webinars, and there are, you know, all kinds of subjects. So this is a great way to learn about stuff and maybe even get some different points of view. So let's move right along. Well, who am I? For those who don't know, I received my novice in '61, so I've been around the block a couple of times. I'm an MSW out of Purdue. I have a great interest in propagation, and that, of course, flows right into, you know, what's the sun doing, because that affects propagation. I'm now retired. I was an RF design engineer for Motorola and then Raytheon, which initially was Magnavox, and went through a couple of name changes and ended up at Raytheon. So I don't have to go to work anymore, and that's kind of nice. So just some opening comments. We're in the decline of cycle 24. I think that's probably quite obvious to everyone. So the big questions, you know, what's cycle 25 going to do, and what about cycle 26? What's it going to do? Do we have any insight into what these two solar cycles may do for us? Now, there are lots of news about where we're headed. You can see it in the various news services. And the next slide kind of sets the tone for this presentation. And what it is from the American Geophysical Union meeting in December 2008, it listed all the predictions at the time that there were for cycle 24, the one that we're in the decline on. As you can see, there are many different predictions. The colors refer to the methodology in coming up with the prediction. 1, 2, 3, 4. There's 6 methodologies trying to predict what a solar cycle does. The 2 asterisk ones we'll talk about a little bit later. And because there's so many the different methodologies, that led to many predictions. I think if you count those up, there's probably around 50 or so. And the predictions went from a low of 40, way on the left there, all the way to 185 on the right. and everything in between. Let me turn off my little thing here. There we go. Get it out of the picture. There we go. So what the previous slide tells us is we don't fully understand the process inside the sun that makes solar cycles. We got a lot of good ideas on it, but we still haven't pinned it down yet to anything that really gives us confidence for a prediction. So when you're reading all these news service stories, I just caution you that you know, there's no validation on what's going to happen, because it takes a number of years to validate new solar theories. And we'll talk about that a little bit too with that dynamo model. As for predictions, the precursor methodologies appear to give the best results. At least that's what several solar scientists say, and I've had good luck with the precursor methods too. We'll talk about those later too. Also, hopefully one day the dynamo model will take over. It's a true physical model, and if we understand everything enough, that then we'll have a good physical model of what's going on inside the sun. Now, my presentation is limited to several of the well-known and hopefully pertinent solar parameters. I'm just going to talk about solar parameters and the effect on propagation. That'll be towards the end of the presentation. I'm not going to talk anything about climate or anything like that. It's just solar issues and how that impacts propagation. If you're real interested in digging much deeper into solar topics, I suggest going to Dr. Leif Svalgaard's website there, www.leif.org research. Lots of papers, lots of good information, and lots of good historical information on solar cycles, etc. So for those interested, go after it. Okay, here's just a quick view of what the status of cycle 24 is in terms of the 10.7 centimeter solar flux. I think you can see my pointer. Of course, cycle 24 went through two peaks. I think most people are aware of that. The second peak gave really good high band propagation, and high bands being 15, 12, and 10 meters. And we even got some good 6-meter F2 propagation from the second peak, because it maximized around the fall and winter when the northern hemisphere ionosphere is the most robust. Now cycle 24 is definitely on the way down, and most people are predicting solar min around 2020. You can see that's what that red line kind of heads for 2020 when it bottoms out. I just wanted to make a quick point that 10.7 centimeter solar flux, just like sunspots, are a proxy for the true ionizing radiation. Just remember that, and that helps maybe keep you out of trouble. So why did cycle 24 have two peaks? Well, if we look back, we'll see that 23 also had two peaks. Cycle 22, which was centered around 1990, it had two peaks also. What we're looking at is the sunspots in the northern and the southern hemisphere of the sun. And you can see what's happening is the two peaks are because of the two hemispheres of the sun are becoming more out of phase. So what's happened for the past several cycles is the northern hemisphere was most productive during the early part of a solar cycle, and then the southern hemisphere took over after that, and that caused the second peak. I make a comment about we didn't see any two peaks in any other solar cycles prior to or during the Dalton minimum, so just remember that. We'll get to that in a little bit. Okay, let's go off on kind of a tangent here real quick. Remember, I presented cycle 24 in terms of the 10.7 centimeter solar flux. Now, I could have presented it in terms of sunspot number, but, well, there could be some confusion now. And that's because, well, we've got new sunspot numbers. For example, here's cycle 24 in terms of sunspots, and it comes from the data comes from the Royal Observatory of Belgium. They're the official guys for sunspot numbers. And just a side comment that Marshall Space Flight Center, they have a lot of good solar stuff. They use this data. So if you look at cycle 24 there way on the right, the second peak ended up at a smooth sunspot number of about 115. So just remember that. Here's some other data on cycle 24 sunspots from a Space Weather Prediction Center, which is part of NOAA. There's cycle 24 there on the right, and its peak, according to their data, is at a smooth sunspot number of about 80. So what's going on here? Why is there a difference between the Royal Observatory of Belgium and the Space Weather Prediction Center? Well, like I said, we have new sunspot numbers. And there's always been a concern about the quality of the sunspot data, especially some of the early years. Also, you know, the equation for the Wolf sunspot number, that's the daily sunspot number, is 10 times the groups plus the total number of individual spots, S, and then you multiply that by a variable scaling factor. Now, nowadays we kind of call a variable scaling factor a fudge factor. And what it's trying to do is take into account the telescope used. You know, a more powerful telescope would probably see more individual spots. The viewing conditions, you know, is it hazy out? Is it nice and clear? Is it cloudy? So maybe some observatories don't provide data. And there's this last one, observer bias. So the bottom line in all this is counting sunspots is very subjective. And again, it's especially because of trying to accurately count the number of individual spots. That's a tough job. So back in the early 90s, two fellows named Hoyt and Shatton devised the group sunspot number. And what it does is it only uses the number of sunspot groups, which should be easier to count. Now, they also discovered more old data to fill in gaps in the record, so that was quite productive, just that aspect. We got more data to verify what was going on, to validate what was going on back in the earlier days. Now, due to the way they derived the group sunspot number, the ratio of the group sunspot number to R should be 1, okay? Well, here's what the results show when you take the group sunspot number and divide it by R. Well, we don't get 1. In fact, we get, it looks like 3 separate time periods. And what they are is they're based on the observers during those time periods. And what that told everyone that there were observer biases. You can see that Schwab and Wolf were kind of consistent. Now there's lots of more scatter in the early data, and we kind of would expect that, I suppose, because of you know, the equipment used way back in the 1700s, etc. The Wolf and Brunner, his assistant, and the Waldemar, of course, the scatter's less, but obviously there's something, they were counting things different. So these biases, along with some other issues, were corrected in the new data. Now here's a plot of the old sunspot data versus the new sunspot data. I did this for only 1950 to the present, basically our lifetimes. And as you can see, the old data is lower, whereas the new data is much higher. Now, one of the anchor points in the old sunspot data was the peak of cycle 19, the biggest in recorded history. And that was a smooth sunspot number of 201, and you can see that's what the blue data suggests. But the new data has the peak up around 285. Now, if I would have shown all the other data back to 1750 or so, Not all of it went up. Some of it went down. So you can find all that data on websites. So just kind of wrapping up this new sunspot number stuff. The plot on slide 7, which is the Royal Observatory of Belgium, reports the new sunspot numbers, which has been called version 2, V2, whereas the Space Weather Prediction Center plot on slide 8 reports the old sunspot numbers called version 1. Now I sent an email to the SWPC asking when they might start reporting the new numbers, but never heard from them, so not sure what to say. Again, this entire effort was done, to make our records more accurate. And of course that's important in trying to use sunspots to measure and predict other issues. The V1 and the V2 data is available at that website. That's the Royal Observatory of Belgium website. And if you want to read a lot more detail on all this new sunspot number stuff, you can go to my website, click on the monthly feature on the left, and then scroll down to the April feature. Or you can read about it in the October 2016 QST, which should be out in probably several weeks, I guess. It's pretty fascinating how they did all that, and why they believe that we now have a much more accurate record of sunspots going back to the cycle 1, which is around 1750 or so. So here's something I've shown quite a bit before. It's the historical sunspot data, the maximum smooth sunspot number of all 24 cycles. You can see there are 3 periods of large sunspot cycles, 2 periods of small sunspot cycles, and it looks like we're headed for some small cycles. Of course, you have to apply the old rule of thumb from the financial markets. Past performance doesn't guarantee future results. So, but if the sun kind of heads in the same trend, it looks like we're headed for some small cycles. Now, cycle 5, 6, and 7 were quite low. That's what's called the Dalton minimum, because of the gentleman who identified it. Cycles 12 through 16 or so, that's kind of another low period of sunspots. I thought at one time I saw a name for that, but I can't find it, so it's just an unnamed minimum, and we'll probably have to leave it at that. So the question is, how small do we think the next sunspot cycles will be? Are they going to be kind of like a Dalton minimum with just low sunspot numbers around 50, a maximum smooth sunspot number around 50? Or are they going to be a Maunder type minimum with essentially no sunspots? And this is a plot here of, like it says, 400 years of sunspot observations. You can see the Dalton minimum. There's the what's called the modern maximum, and there's the Maunder minimum when there was hardly any sunspots. And there's been a lot of technical papers on that, and I think it's pretty well established that indeed there weren't any sunspots, even though it was back in this 1650 to 1700 when instruments were kind of new, telescopes were kind of new. But I think it's well established that we had a dearth of sunspots back then. Now here's another confusing thing. If the new sunspots aren't confusing enough, the definition of a grand solar minimum, as best as I can tell, is defined as a period of greatly depressed activity. So what the heck does that mean? No doubt that the Maunder minimum was a period of greatly depressed activity. What about the Dalton minimum? Is that greatly depressed or not? I've seen some scientists say that the Dalton minimum is a grand solar minimum, and I've seen some people, some scientists say it isn't. So that's confusing, but unfortunately we're going to have to live with it. And, just remember that maybe some people call it this and some people don't, kind of like the planet okay, the X-planet, the Pluto. Okay, here's just a look back even farther in time, back to 800 AD, historical grand minimums, and this is derived by looking at the carbon-14, the deposition of carbon-14 in tree rings. I've not found an update to this, which would extend it, up to the current dates. It looks like the data ends about 1950 or so. So it'd be nice to, find that, but there was a gentleman who took a heck of a long time to look for me. I don't remember his call at the moment. I should have saved it, but I didn't. But we just didn't find anything. Now there's a solar scientist named Usaskin, and in the paper that I'm going to give as a reference at the end of this presentation, he lists that there have been about 27 grand minimums in the past 11,000 years. It includes that Oort minimum right here, but it doesn't include Dalton, which is kind of funny, so I'm not sure what to say about that. And what we're looking at is just, is there a lot of carbon-14 deposited? If it is, that's a solar minimum period. If there's not a lot of carbon-14 deposited in the tree rings, that's a solar maximum. Also, Usaskin says there have been about 19 grand maximums in the past 11,000 years. Cycle 19 era is the only recent one in his list, and that's in here. It's too bad we don't have that data. There was a medieval maximum from about 1100 to 1250 right in here, and another around 920 to 980, and a whole bunch before that. So what this all says is, we've had lots of grand minimums, we've had lots of grand maximums, and it looks like we're going to probably continue to see those as time progresses. Okay, now let's look at some pertinent solar data. This is the sun's polar magnetic field. It's plotting the strength of it. And what you can see is, well, the red trend lines show that the strength of the polar magnetic field is decreasing. Now, if you remember, when we reach solar maximum, the magnetic field of the sun flips, and that's why it goes through this zero line right here. So there's the peak of cycle 21, there's the peak of cycle 22, peak of cycle 23, the peak of cycle 24. But the trend here is the sun's magnetic field is weakening. Now, another way to confirm that is through cosmic rays. So the zero on the vertical axis here is the overall average neutron count. And we count neutrons because cosmic rays come down, and when they collide with atmospheric constituents, they create a shower of particles, and one of those is neutrons. Now, when the data is positive, that means there are more neutrons, which occurs when the sun's magnetic field is weak, solar minimum. On the other hand, when there's a negative values down here, that means there are less neutrons, which occurs when the sun's magnetic field is strong, solar maximum. So at solar minimum, a lot more cosmic rays are let into the Earth's atmosphere. At solar maximum, not so many. Now you can see what's happening, at least in our recorded data, which basically just extends from the space age, kind of. That we're seeing more and more neutrons. We're counting more of them, And I'm sure cycle 24 is we're gonna see a lot more too. And that trend, because it's going positive, shows that also confirms that the sun's magnetic field is getting weaker. Now there's something tied to D-region ionization. These cosmic rays are energetic protons. They're very energetic, and they can get down to tens of kilometers into the atmosphere. And what that means is they do cause some D-region ionization, even at night. And so that raises the question, can a solar minimum be so deep that it's going to hurt 160 meters? Maybe we'll find out here as we progress down on cycle 24 and see what it does. Okay, so just a quick summary on the sun's polar fields and cosmic rays, and the trends indicate that the sun's magnetic field is weakening, and that likely translates to a smaller solar cycle. But still, that doesn't really tell us how small. Well, that brings us to a paper in 2010 by Livingston and Penn. And what they did is they measured the strength of the magnetic field around sunspots. And you do that by a technique called Zeeman splitting, where the iron spectral line splits into two, and the amount of splitting tells you how strong the magnetic field is. Now here's the data that was presented in 2010, and this got lots of press. We know that we can't see sunspots if the magnetic field strength is less than 1500 Gauss. So if we extrapolate that data, it suggests that we would not see any sunspots by 2016. Well, so that led everybody to the conclusion that, wow, we're headed towards a Maunder minimum because we're not going to see any sunspots. If that's what a Maunder minimum is just not seeing sunspots, but the process still goes on. Well, here's the updated data, and the data is the same. Just note that the vertical axis has been expanded quite a bit. And what's happened is it looks like the strength of those magnetic fields around the sunspots has leveled off. So what that suggests, at least for the data we have, is that the sunspots won't disappear. What that tells us that maybe the next maximum, cycle 25, will just be a low number of sunspots, not zero sunspots. Okay, let's get into sunspot cycle predictions. As I mentioned earlier, precursor methodologies seem to be the ones that kind of give us the best results. And there's several precursor methods. One is the duration of solar min. It predicts the next maximum. We'll look at the number of days with zero sunspots. We'll look at the planetary A index, and we'll even take a look at is there any pattern to sunspot cycles as we approach the Dalton and Maunder minimums, and does it look anything like what's happening right now? Then we'll talk about the dynamo model for a little bit. Okay, for all recorded history, if you look at the data, the duration of solar min and the next maximum, they're out of phase. In other words, if the duration of a solar min is very long, that means the next cycle is going to be small. Likewise, if it's a short period at solar min, the next cycle is going to be large. So here's a plot of the data, and I define the duration of solar min as when the smooth sunspot number, R12, is less than or equal to 20. You can see that there's a pretty good trend going on. The longer time you spend at solar minimum, the smaller the next cycle is. Cycle 24 kind of fit into that pretty nice. So what we need to do is keep an eye on the length of minimum between cycles 24 and 25. Now this brings up a good question. What's the physical reason for this correlation? Well, I don't think anyone understands why, which could bring up the suggestion that this data is just kind of a coincidence. But I think we'll just have to wait and see what happens with the min between cycle 24 and 25, and eventually see what cycle 25 does. Again, the R-squared value is, nothing terrific, but you can see there's an obvious trend in the data. Okay, how about days with 0 sunspots? Well, this received a lot of attention during the last solar minimum between cycle 23 and 24. And it's starting to receive a lot of attention now as we near solar min between 24 and 25. There's been lots of talk about 0 sunspot days, but what's the data really look like? So what I did is went back to 1950 and looked at the number of sunspots for each day. And what I did is counted the total number of 0 sunspot days in a year. So the top plot is just the solar cycle. You can see it starts with cycle 19, goes through cycle 24. Now the horizontal axis for the bottom plot, which is the number of days of 0 sunspots by year, the horizontal axis is the same. And I drew those red lines in there showing that the days with 0 sunspots usually start around solar minimum, way down there, and it kind of shows that there's usually maybe 4 years or so of days with 0 sunspots. Now, well, okay, let me mention that so far in 2016, at least as of a couple days ago, we only had 20 days. So there's more data to be collected there as we progress towards solar minimum. Yeah, okay. So what I did is I took my data. Well, let's go back to that there, and we would hope that the number of days with 0 sunspots would maybe tell us what cycle 25 is going to do. But you can see that we got a problem. You can see that for the min before cycle 20, we had 209 total days. But when you look at the min before cycle 19, it was a very big cycle. You would figure that there wouldn't be many days with 0 sunspots, but well, it was even higher than the minimum before cycle 20. So that kind of says, well, this data may not tell us anything. And when you kind of do a scatter diagram of the next maximum versus 0 sunspots, well, the correlation is very poor. Now, there's only 6 data points, so I'm not sure I'd even rely on it if it showed very good correlation. Now, maybe one of the problems is when we count 0 sunspot days, that really means only on the visible disk of the sun. We're not talking anything about what's going on the backside. So that could be something that's really not going to tell us a lot unless we can count sunspots and see them on the backside, which we have the stereo guys and the I think stereo A has been running for quite a while. Stereo B, for some wild reason, just came back online after a couple years of silence. So maybe we're going to get some good data here that kind of supplements these 0 sunspot days, and it truly counts when the sun is totally spotless. Maybe we'll find out it's never totally spotless. Okay, so wrapping up this zero sunspot stuff, it doesn't look like there's a lot of correlation to, or it doesn't look like we're going to have any confidence in telling what cycle 25 is going to be like. This approach to the min between 24 and 25 started a couple of years earlier than the previous solar mins. And what that just may mean is we'll have a record number of days with zero sunspots, but it's not real clear to me, at least, if that says anything about the cycle 25 maximum or the future cycles. Okay, one of the other precursors is the A index. In other words, the geomagnetic field activity. And what's plotted here is in yellow is the annual sunspot number. And you can see there's cycle, that must be 17, 18, 19, 21, 22, and there's 23. The data only went out to 2000. The red data is the number of days in the year with when the AP index was greater than 40, which means it's disturbed, very unsettled. And if you look at this plot, you'll see at solar min, the A index, the total number of days is minimizes at solar min. And you can see that, like before the cycle 19, the big cycle, it was up around, looked like 15. For a small cycle, it was even a little bit lower. And for our cycle that we just went through, which was even lower than cycle 20, it was even lower. So there appears to be a good correlation, or at least a decent correlation between how quiet solar min is and the next solar cycle. So this would be a good one for someone to track, and you know, it'd be interesting to see what's going on. Now the data is all there. You just got to go collect it and you know, keep plotting it and see what happens. Okay, what about any patterns of the sunspot cycles prior to a grand minimum? Is there a pattern that we're seeing that we saw back in the Dalton min and the Maunder min? So what's the data say for that? Well, here's a plot that shows in blue cycles 3 through 8. You can see the Dalton minimum was cycle 5, 6, and 7. Here's 3, 4, 5, 6, and 7. And here on the same kind of scale on the horizontal axis is cycles 22, 23, and 24. And there's kind of a pattern there, but you know, like I say in the text below, I don't think I'd go to court with this. Also note that there was a long period between cycle 4 and cycle 5. In fact, there's evidence that we may have missed a cycle between cycle 4 and 5. Actually, there could have been a little one in here, and if that's true, that kind of might kind of throw things up, kind of screws everything up. You'd have to go relook at all this stuff. So it doesn't look like, you know, that there's a lot of confidence in saying that we're seeing the same pattern as the Dalton minimum. The only way to verify that, of course, is to wait and see what happens with cycle 25 and 26. What about prior to the Maunder minimum? What did solar cycles look like? It looks like going into a Maunder minimum that there was a much more abrupt transition. It had a large cycle, looks like 100 and something, and then we immediately just dropped down, and that was, you know, looks like it's left maybe 35 or so, and then that was it. But of course, you got to say how good was the data back in 1610, 1620, or something like that. So the only conclusion I can make is if anything, the current data looks more like a Dalton min of smaller solar cycles. That's the pattern it looks like. Okay, the dynamo model. If you remember, the solar scientists who predicted a very large cycle 24 used a one-cell pattern of convection inside the sun. Well, her prediction was the 185, I believe it was, which was way off. There's been research going on. It looks like it really may be a two-cell pattern of how the plasma flows in the sun. It goes deep to the equator, it comes up, and then it goes back down deep at the higher latitudes and comes back, and there's, of course, a cell pattern in each of the hemispheres, which they could be different because that's why we have two peaks in a solar cycle. They're just not doing the same thing at the same time. So here's what the two-cell pattern looks like. It looks like there is a one cell more at the surface, and then a deeper cell, convection cells, or convection pattern. I hope this will improve the dynamo model, and again, it's going to take a number of years to validate any theory that comes out of this. Okay, let's do a quick summary here. I personally believe the only conclusion we can make right now with some confidence is that we're headed for some small cycles. That's what it looks like to me. And the solar polar fields and the cosmic rays support this. And the concept of disappearing sunspots supports low cycles, not zero sunspots. Then again, the sun's going to do what it wants to do, and regardless of what we think. The number of days with zero sunspots just doesn't seem to help at the moment. We'll have to wait and see what happens. And I think the best indicator of cycle 25 is going to be the length of solar min between 24 and 25, and how quiet it is at solar minimum. That may give us an early heads up for cycle 25. Okay, now let's tie this into propagation. First of all, we'll talk about the near future, like for the next a year or so. Of course, the higher bands, 15, 12, and 10, will pick up a bit in the fall. That's because in the northern hemisphere, the fall and winter months give us the most ionization for the solar radiation. Unfortunately, after that, as we progress next spring and summer, I think F2 propagation is going to really decline. The only hope for those higher bands in 6 meters is sporadic E in the summer, although there's a big caveat with that. Sporadic E this summer on 6 meters was not good at all. What's going on there, who knows. The lower band should be good. Remember my comment about cosmic rays, and maybe a solar min could be too deep. Keep our eyes on that. But 20 and 17 should still offer worldwide propagation, mostly during the daylight hours. So those are the bands that will hang in there for the good DXing, in addition to the lower bands. Okay, so what if we have a Maunder min, or what if we have a Dalton minimum where we have just low sunspots, or what if we have a Maunder min with zero sunspots? Well, if we enter a Dalton min, the propagation's going to be somewhat worse than cycle 24 was. We'll still have some higher band openings, but they'll be few and probably far between. Now, if we enter a Maunder min, we'll have propagation similar to the minimum between cycle 23 and 24. The higher bands will mostly be noise. There'll still be sporadic E. At least the data suggests that the sporadic E is independent of a solar cycle. At least the data we have. The lower band should be good, and again, 20 and 17 will offer worldwide openings. Now, I referenced some reading material and nice long paper by Usaskin, A History of Solar Activity Over Millennia. If you just put that title in with his name and into Google, it will come up, and it's a PDF. It's about a 70-page document, so there's a lot of good stuff in there. And if you want to learn a lot about solar cycles, Dr. Hathaway has a paper called The Solar Cycle, and if you put that title and his name in, you'll end up with a PDF. It's also around, it's about 65 pages. Lots of good information in both of those, and like I said before, if you want to get into deeper solar subjects and research, go to Dr. Svalgaard's website that I referenced at the beginning of this presentation. On here, okay. Okay, I got a couple bonus slides. We got some time, and I thought I'd just show this one. What this shows is, oops, uh-oh, watch out there, kitty cat. Whoops, come here, don't step on the keyboard. What this shows is the number of months that the various solar mins were below a smooth sunspot number of 20. And if you look at the color codes, the pinkish and the green and the blue and the black and the dark blue, those were you know, mins between 18 and 19, 19 and 20, 20, 21, 21, 22, 22 and 23. And those solar mins lasted about 2 years, 24 months or so. And then along came the solar min between 23 and 24, and it went on for, looks like 56 months, which is, you know, about a little over 4 years. Buffy, you're going to have to move here. So we kind of grew up experiencing short solar mins until the last minimum, and it showed us maybe what we can expect for the next couple solar cycles. Be nice to have maybe just Dalton type minimum, but who knows. Here's a slide on the F2 region variability. On the right is the maximum usable frequency over the Wallops Island ionoson at 1700 UTC for every day in August 2009. Now, during August 2009, as you can see on the left plot, the solar flux was pretty constant. There weren't any sunspots, which is the red data, and the AP index was kind of not too bad. But even though the solar flux was constant, there were no sunspots, and the A index was low. There was still a lot of variation in the F2 region, and that's what we can expect. That's because the solar radiation certainly instigates ionization, but there are two other processes that determine what the ultimate ionization is going to be. And also note that even though we had 0 sunspots for that period, apparently there's still you know, ionising radiation, which is basically extreme ultraviolet, because we did have you know, we did have an ionosphere up there. In fact, with no sunspots, it looks like the ionosphere, you know, on average is going to give us a MUF about 15 megahertz, so 20 meters will still be there, and you can see even there'll be some days when 17. So that's the basis for me saying, even if we go into a Maunder minimum, 20 and 17 will probably still be there. Now, one thing that another thing we don't understand is the sun appears to have changed. So this is just a preliminary plot here to set up the next slide. And what it is showing the radiation from the sun over all the wavelengths at which it radiates. It radiates from you know, tenths of a nanometer wavelengths to well over 2,000 nanometers. Now the sun's most of the highest radiation is in the visible light spectrum. Of course, the visible light has nothing to do with ionizing the atmosphere. the little green box here shows the wavelengths that ionize the D, E, and F regions, and that goes from about 0.1 nanometers up to about 100 nanometers. Now, from this, maybe you've heard of something called the solar constant, and that leads us into the next graph. So what this plot shows is what's called TSI, the total solar irradiance, which means how much does the sun radiate in terms of watts per meter squared over all the wavelengths it radiates at. And this is what basically these colors right here. Those are the different instruments that measure total solar irradiance. You can see that the total solar irradiance only changes by very little over a solar cycle, from 1361.7 watts per meter squared down to 1360.5. That's only a change of about 0.07%. So that's why these numbers here are kind of considered as the solar constant. That's because of the total solar irradiance doesn't change over a solar cycle. But we know that the ionosphere changes by quite a bit, and that's because if we go back to the previous plot, there's not compared to visible light, there's not a lot of flux at ionizing wavelengths. It's enough to ionize the ionosphere, and the ionosphere changes by at least a factor of 5 over a solar cycle. But of course, the changes down here, because they're so small, get swamped down in this total average. But you can see that, there's also other kind of solar factors are plotted. The sunspot number is plotted in this mess of curves. Manganese 2 at about 280 nanometers is plotted. That's ultraviolet radiation. The group sunspot number, the sunspot number version 2, remember version 1, version 2, the 10.7 centimeter solar flux, and the sunspot area. And you can see that during cycle 23, all of those measurements kind of lined up very well. Of course, the developer of this, the maker of this plot had to scale everything to get them to fall on top of each other, but that's what happened. But you can see in cycle 24, the total solar irradiance measurements are very similar between all these instruments, but the other plots are, there's a lot less sunspots for the total solar irradiance that occurred. So there's something going on in the sun that's changed, and I'm not sure anybody knows what's going on yet. So that was the end. Whoops, Buffy. No problem with a cat here. That's all I had. So I'll go back up a little bit, and we can hit other slides if someone has a question, I guess.
Okay, very good. Thank you, Carl. So if you have any questions for Carl, there's a little questions box. Type your question in there, hit send, and we'll pick it up and pass it along to Carl. And don't have anything in at the moment, so we'll just wait another minute or so and see if something comes in. But
okay.
I was listening to you with your cats there, and it reminded me of, I'll send you a picture earlier this summer. I was in Zambia, and I got to go to a game park and pet 2 tame cheetahs. At least they were tame when I was there, thankfully.
Yeah, right. They'd been fed before, hopefully, right?
Yeah, exactly. And they purr just like a regular cat, so.
Yeah.
Okay, well, boy, you must have answered everyone's questions, because I see nothing coming in here at all, which is great. And of course, you are always, here we go. This is something I forgot to mention earlier. The presentation has been recorded, and it will be posted on the WWROF webpage. And that should be up in the next couple of days if anyone wants to watch that. Or if someone missed it, they can go there. Question from Daniel. What's your best guess as to when cycle 24 will bottom out?
Well, let's see, hold on here. Let me go back to, oh man, how do I get there quick? I don't know. I don't. Yeah, we'll get there. The plot I showed of the status of cycle 24, there it is. The red line is kind of, no, it's not the right one. Oh, wrong way. Yeah, there it is. The red line is the predicted 10.7 solar flux, and there's 2019 starts right here, January, so 2020 is over here. So it looks like around 2020 is the bottom of the next cycle. Of course, a year before that, it's not going to be too much different than the bottom. So probably 2019, 2020, 2021, and maybe even longer will be at solar minimum, depending on what the definition of solar minimum is. Less than smooth sunspot number of 20, which is a solar flux of maybe I don't know, 70 or something like that, or even maybe 70 or so. So 2020 is kind of the ballpark figure for the solar min.
Okay. Jason's wondering, how does the unsettled solar weather of the last couple of years compare to previous cycles?
That's a good question. Man, I saw a paper on that, and I don't remember what the conclusion was. Nuts. I'm sorry, I can't answer that.
Stump the professor, he gets a prize, right?
Yeah, well, I'm getting old and memory goes. Of course,
okay.
Who am I talking to?
Yeah. Okay, Jim K0XV is wondering, will 28 megahertz be a bust even in the good old days? And I imagine the answer is yes, as we continue on down to the bottom of the cycle, right?
Well, it'll be a bust in terms of F2 region propagation. Remember, there's still hope for, sporadic E. There have been many good summers with 10-meter sporadic E, and hopefully we'll have some more of those. So it won't be a total bust. But again, that's going to depend on, what sporadic E does.
Okay. Question from Bob, and I think this is Bob N6TV. Should we continue to enter SSN in propagation prediction programs, or would it be better to use another number?
Yeah, what I would do is, think about this. What's the correlation? What's the model of the ionosphere in our propagation prediction programs? It's the correlation between monthly median ionospheric parameters, like the F2 region critical frequency and stuff like that, and the correlation is to the a smooth solar index. So it certainly looks like to me that we correlated the model of the ionosphere in our propagation predictions to the wrong sunspot numbers, if we believe that the new sunspot numbers are more accurate. Now, I kind of looked at that a while back, and it looks like the error could be several megahertz. So we're maybe talking a band, like 20 meters, 17 meters, 15 meters, 12 meters. So to avoid confusion, I'd input the smooth 10.7 centimeter solar flux, just to avoid confusion between version 1s and version 2. Again, our predictions are statistical over a month's time frame, so you may not even notice that difference. But it seems to me that it'd be best to use 10.7 centimeter solar flux for now.
Okay, looks like maybe this will be the last one. Gary's wondering, given the indicated changes in the sun, will we ever see another cycle 19? And I don't know if that's we literally or if it'll ever happen again.
Yeah. Well, again, we went through, let's see, where are we here? Nope, that's not it. Yeah, shoot, where are we? Ah, shoot. Oh, what are you doing? That's the other cat now. We got 3 cats. Did you ever try and eat a bowl of cereal with milk with 3 cats? Boy, it's a tough one. Whoops, where am I here? Where'd my plot go here? Yeah, right here. It looks like we're headed for a period of small sunspot cycles, but future ham radio operators, probably not us, could see something like cycle 19 in after another 5 cycles down the road, maybe 50 years or so. So if we believe this trend here shown in this plot, then yeah, we're going to have some big cycles again, and one of them could be as big as cycle 19, but I'm sure it's not going to be in our lifetime.
Okay, let's make this the last one. From Jim, good question. Propagation programs seem helpful for short path predictions, but are generally worthless for long path predictions. Any comments?
Yeah, that's a good assessment. Most of the most of the predictions for extremely long distances, like long path, really are based on what's called the control point method. In other words, you kind of look at the ionosphere about 2,000 kilometers from each end, and that's for looking at the F2 region. What that says is you're assuming that those first hops out of each end are about 4,000 kilometers, which is kind of good for the higher bands. It's a little bit less for the lower as you go down in frequency. But what they do is just look at those 2 points and assume if propagation can be supported at those 2 points, 2,000 kilometers from each end, that the whole path can be supported. Well, that's a pretty big assumption, especially for long paths. So that's true, and short of looking at every hop and a prediction, I'm not sure what else you could do. But if you look at every hop, I think you're going to have trouble with loss, because probably a lot of the long path propagation involves chordal hops, which you don't have intermediate ground reflections, and you don't have transits through the absorbing region. So yeah, that's the way our prediction programs were set up, and there's not much we can do. You can always run predictions using a ray tracing program, but that takes a while. So what we got is simple and kind of gives you a general idea.
Okay, well, we've pretty much run out of time here, so Carl, I wanted to thank you once again for coming back and sharing all this great data with us, and it's certainly interesting what's happening, and we'll see how the fall turns out here. Being a low band guy, I'm particularly interested in seeing where we're heading here. So anything else you want to add before we wrap it up?
Nope, just make sure you if you're working on any awards for the higher bands, worked all states, DXCC, worked all zones, whatever, make sure you get on this fall and winter, because it may be the last good opportunity for you for quite a while.
Yeah, good advice. All right, thanks everyone for joining us. I wanted to mention as well, if you have any suggestions for topics or presenters, certainly send me an email. We're always looking for good content to share here, k4zw@verizon.net. Be happy to have your input on that. So with that, thanks everyone. Thank you, Carl. Thanks everyone for joining us, and we'll see you next time. 73s.
Okay.
Bye-bye.
Yep, bye-bye. Bye.